Hello and welcome to today's lesson on experimental design. First thing we have to do when we talk about experimental design is talk about some of the definitions that we have. First, we've got an observational study. That's where, based on the title, the person observes and records information, but there is nothing imposed on the individuals that are being observed. Okay, that is very different than an experiment. In an experiment, we're actively imposing some treatment. We're changing some variable in order to observe the response. Okay, so now, if someone develops this new rabbit food, okay, makes fur soft and shiny, increases energy, 100% of daily vitamins and essential oils, so they're making all of these claims in the commercial for the rabbit food. Okay, can we make these claims? No. What do we have to do to make these claims? We have to do an experiment. We have to prove that these claims are true. Okay, who should we experiment on, or who or what? Rabbits. And what do I test? The type of food. So when you're doing an experiment, you have to answer all of these questions. What am I testing on? What am I testing? How much am I testing in this situation? So the experimental unit is the individual that's being tested on. It could be a car, it could be a person, it could be a plant, animal. We could test a road surface. Okay, so the road surface could be an experimental unit if we're putting coatings on it for longevity. The factor is our explanatory variable. It's what we are imposing into the situation to test overall. And we can have different levels of the factor. When it comes to food, do we give a half cup? Do we give a full cup? Do we give a quarter cup? Okay, so we can have different levels of that factor. And then the response variable is what we want to measure. We want to measure the, shininess of the fur of the rabbit. Does the rabbit seem to have more energy overall? And the treatment is a specific experimental condition applied to the units. So sometimes there can be multiple treatments in an experiment. We can control temperature and light in a classroom and see how that affects students. So there would actually be two treatments. One treatment would be the temperature, the other treatment would be the light, and we could measure different pieces of that. Okay, so now I want to test the new rabbit food. We're going to test it on rabbits. The factor is the type of food. The response variable, how well they grow. Okay, so now, if we're just going to use one rabbit, okay, we use one rabbit, we give it the food, we test it, and shinier, more energy, okay, so we know that this food is better. Okay, there's a problem with that. We need a control group. We need a comparison group in any experiment, okay, to make sure that what we're seeing in the response variable is due to the treatment and not due to the rabbit themselves. Okay, the control group sometimes gets a placebo or dummy treatment. It can be a sugar pill, it can be colored water. It's all based on what you're trying to compare it to, because people can respond to just getting something rather than actually responding to the treatment that's being given. Okay, so now we've got two rabbits. Okay, we're going to use my rabbit Lucky, and we're going to use my friend's rabbit Flash. Okay, my rabbit gets the new food, friend's rabbit gets the old food. Wow, Lucky is bigger, shinier, so hippity hop is better. Okay, we still can't do that. We need, in any experiment, what we call replication. We have to be able to conduct the experiment on enough individuals in both groups so we know it's not based on chance alone. Okay, how about the first 5 rabbits I catch, I'll give the food. Okay, so I catch these first 5 rabbits. I'm giving them the new food. Okay, the old food goes to the 5 rabbits I couldn't catch. Is that a good sample design method? Okay, so, the hippity hop rabbits are bigger, okay, and they might have just been bigger because they were slower and I could catch them. Okay, now here is the best way to separate your individuals. We need randomization. Okay, we're going to place the numbers in a hat. Okay, the first 5 numbers that are pulled get the new treatment. Okay, so now we're doing this in a random fashion. And then the remaining rabbits get the old food. Okay, we need a control group for an experiment. We need randomization for an experiment. And we also need replication. We need to make sure that we're not just doing it on one individual. We are doing it on multiple individuals. Now we could make our claims based on this experimental design. Okay, now, some other terms that we want to have in place for experimental design. Sometimes it's important for blinding. Okay, the method used so the units don't know what treatment they're getting. Okay, because they could respond to the fact that they're getting something new and not responding to the piece themselves. It's what we call that placebo effect. Okay, so it's important to make sure that the experimental units don't know what group they're in, if at all possible. And sometimes when we're talking about medical trials, we want to go a step further into what we call a double-blind experiment, where neither the person giving the treatment or the person receiving the treatment knows what they're getting. Okay, and this is really important in medical trials because the person giving the treatment can affect the respondent just by the interaction that occurs. Okay, now, can we make this claim? Increases energy for all types of rabbits. And the answer is no. We can only make the claim based on the type of individual that's experimented on. Okay, so we have to think about population, like when we talk about a survey. So if our sample comes from a specific population, Minnetonka High School, we can only make claims about that population or Minnetonka High School. So now, we've talked about these briefly. Our principles of experimental design, the control group, okay, controls for extraneous variables. Okay, we need someone to control too, either a placebo or an old treatment. We need replication. We need to have as many subjects as possible so we know that it's based on the treatment and not based on the subject themselves. And we need randomization, the use of chance to assign subjects into treatment groups. Okay, the only way to show cause and effect is with a well-designed, well-controlled experiment. Okay, it's so important. I want to PowerPoint shout at you here with these extra pieces. Okay, the only way to show cause and effect is with a well-designed, well-controlled experiment. So let's look at a few examples here to make sure we can identify the pieces that we're looking at. So we've got a farm product manufacturer wants to determine if the yield of a crop is different when the soil is treated with 3 different types of fertilizers. So what's the experimental unit? What's being tested on? The plots of land. What are the factors? What are we manipulating? The types of fertilizer. What are the levels? Okay, the fertilizer types, A, B, and C are the levels in this experiment. What's the response variable? The yield or growth of the crop. How many treatments are there? 3. Okay, treatments are your factors times your levels. Okay, another example. We want to test cake pans to see what bakes best. Best being an even baking. Okay, test aluminum, glass, plastic pans in both glass and electronic ovens. Okay, so what are we experimenting on here? This is one of the tougher ones. We're experimenting on cake batter. What are the factors? Okay, and there's two. Type of pan, type of oven. What are the levels? 3 levels of pan, 2 levels of oven. Okay, so what's the response variable? Okay, the even in the bakingness. Number of treatments, 6. Levels times factors gives us the number of treatments that are being imposed in the experiment. Okay, now we'll go through one more here. Farm product manufacturer wants to determine the yield of crops different when the soil is treated with 3 different fertilizers. Why is the same type of seed used on all 15 plots? Okay, it's a control of the experiment. We want to control as many variables as we possibly can, so that's why we want to use the same type of seed, because otherwise it could be based on the seed and not based on the fertilizer. Other potential extraneous variables, types of soil, amount of water, terrain, there are all different things that you have to think about that can affect the outcome of the experiment. Does this have a placebo? No. Okay, we're comparing the 3 fertilizers. We want to see which fertilizer works best, so we don't have to compare to something with no fertilizer. Okay, we're just comparing the fertilizers themselves. One thing that we always talk about is we can draw a diagram to show what's happening in an experiment. So we can use the experimental design diagram where we start with our explanatory variable. Randomization happens at this first spot. So you want to have a random assignment on your explanatory variable side into your 3 groups. And then we come back together to measure the response in the end. Okay, so once again, the randomization is the important part of the process. Okay, now notice when we randomize, we are not getting equal groups in each spot. Okay, we can see the blues and the pinks can be different in each one. Okay, so randomization is not perfect. Okay, but it's the best method that we have overall. Okay, now block design is just like our stratifying in survey situations. So when we have a block design experiment, what we want to do is we want to separate the groups first and then randomly assign to the treatments before we measure the response. Okay, so the random assignment happens at that level. So what we actually do, put them into their homogeneous groups, separate blues and pinks. Okay, and once we've separated these groups out, then we start assigning them into the treatment groups. Okay, so we separate treatment A, half a blue, treatment B, half a blue. Okay, but it's still a random assignment at that piece. Okay, matched pairs. Okay, one of our last types of experimental design. Okay, this is where you're going to match individuals that are as closely related as possible. You know, this is where you could work with twins in a situation like this, where you're separating them out. One person gets one treatment, the other person gets the other. Or you could have each individual do both in a random order. Treatment 1, treatment 2, or treatment 2, treatment 1. So if we do a block design, okay, we're going to organize based on characteristics. Okay, we want blue happy, blue sad, pink happy, pink sad, you know, no emotion for that other one. And then once we have them paired up properly, then we're going to randomly pick, this could be a coin flip, to pick who gets A and who gets B to finish the experiment. Okay, our last piece, talking about issues with experiments. The number one issue is a confounding variable. It's a variable outside of what we measured that can have an effect on the response, okay, based on the difference between that and the explanatory variable. Okay, so we can't separate it from the effects of the explanatory variable. So when we're measuring education in different areas, education levels, education outcomes, the one thing that's a confounding variable is the financial status of the families. If some are more influent than others, the financial status of the family cannot be separated from the effects on education from the school that an individual goes to. Okay, so now we're doing this test, we're separating the individuals. Okay, we're doing it grouped based on gender because we understand that one group's assigned to treatment A, the other group assigned to treatment B. What's wrong with this experiment? Okay, in this case, treatment and group are confounded because the males get treatment A, the females get treatment B. We don't know if the response is based on gender or based on the treatment. So that would be the problem in that situation. Okay, now, just finishing these pieces up. Okay, we've got this experiment. Okay, no treatment imposed, so it's not an experiment, more of an observational study. Okay, and age is a potential confounding variable. Okay, word processing programs to help type a little bit faster. 100 volunteers are randomly assigned to one of 4 programs. Is this an experiment? Yes, a treatment is imposed. Type of design, completely random. Factors are the word processing program with the multiple levels, and the response is the speed. Is there a potential confounding variable? No, when we completely randomize, we eliminate that situation. Okay, you could do a block design if you want to work on that piece. Okay. So what we're going to do is we're just going to jump through this quick. Okay, randomization helps us reduce bias. Blocking helps reduce variability. Is there another way to reduce variability? Okay, sample size. Larger samples, less variable overall. And this just kind of shows you what can happen in different experiments. Okay, you can have less variability and hit the target, less variability and not hit the target. Okay, so here we've got high bias, high variability. We're not hitting the target. We're really spread out. In this next situation, you've got high bias. You're not hitting the target, but your variability is very small. You can have low bias. The middle of your product is hitting the target, okay, but high variability. And then this last one is our best case scenario, low bias and low variability. That completes our lesson for today. Thank you and have a good day.